Okay, class. We are going to cover chapter 6. We're going to start off with a review of power series. We're going to go over just some of the particulars. You should have gone over this stuff in Calculus 2, but it's probably been a while since you've seen some series. So we're going to go over them, and we're going to talk about some things that are probably considered new to you that are going to help us to start to solve questions and problems when we're trying to solve our DEs. So let's consider the general form of a polynomial. Okay, so we know polynomials have things like degrees, leading terms, coefficients, constant terms, things like that. So the general form of a polynomial looks like this, right? It's finite. It has at most n plus 1 terms. Right, you have your n terms plus one more because we start at 0, not at 1. We have a constant, we have coefficients times all of our variable terms, and everything is raised to a power. Okay, here we have a power of 1, here it's a power of 0. You guys should be pretty familiar with this, right? So what we're going to do is we're going to take this idea of a polynomial and we will extend it to an infinite number of terms, basically. And what that is what we call our power series, right? So if instead of calling these A naughts or AIs for the polynomial term, I'll call them CIs. So C0, C1, C2 for the coefficients. And then I'm going to increase in power, right? Same thing here. If I wrote this the other way, I would be increasing in power, but standard form of a polynomial, we write it in descending order. For series, we write them in ascending order because we start at 0, right? So again, this is my index. This is my ending value. These represent my coefficients, and these are my power terms. Okay, so this is a standard, what we call Maclaurin power series. This value right here, this c sub n x to the n power, is called our, well, it doesn't really have a name, so we just call it the general term, right? This is the general term that tells us what our series looks like, okay? So this is the lower index of summation. This is where we start, this is where we end, and this is the general term, right? So again, this is the Maclaurin series because this is what a power series looks like when it's centered at 0. We talked about that a couple of videos ago. But generally we center a series around a value A. Okay, so when I'm centered around 0, the origin, it will look like this. When I center it about a value, it changes slightly to look like this. Okay, so this is more representative of what we would be looking at. Okay, so here I have x minus A. Everywhere the x comes up, so my general term changes slightly. The coefficient indices all remain the same. The power indices all remain the same. The only thing different is that it's an x minus a term everywhere instead of an x to the n term everywhere. So let's say that y is this series. Okay, so again, remember, we use series to approximate some function. Okay, so if I just take the standard form and I call that a function, okay, then I can just say that y is the same as this series. I can start to do my basic things to y, like differentiate it. Okay, so again, this is a polynomial. I can differentiate this polynomial term by term, every single term. Okay, so if I differentiate every single term, I get out a new series. Okay, so again, notice that C0 goes away, C1 turns into the constant. I got a 2C2. This power drops down by 1. Apologies, this should be x minus a. I don't know how that came about. But this should be, right, if there was another term, this is what this one would look like. But again, this would be a subtraction. So if you notice that my general value here, okay, my general term, looks like my previous general term if I had differentiated it with respect to x. So again, if I pull down the n, okay, NCN, and then drop this down 1 power, I do that everywhere, right? So I can differentiate the general term of my series. Again, also notice here that this still starts at 0, okay? But what happened here? At 0, the 0 term dropped off. Because what happens when I start at 0? I got 0 times all of this stuff, which goes away, which is exactly what happened. And this constant term from y dropped off. So I have 0 plus, and then now my index now starts at 1 because I've evaluated 1, and then I am now starting at the 1 term because I evaluated the 0 term, I guess I should say. And so now I have the 1 term. So we all know that 0 plus something is nothing, so I don't have to write it like this. I can just say that y prime is equal to this series starting at 1. Okay. So if I decide to differentiate again, I do the exact same thing. This will now start at 2 because the previous constant term will drop off. Okay. This n minus 1 will come down and multiply, and this power will reduce by 1. Okay. Same thing for the third derivative. Okay, the n minus 2 comes in. This drops down by 1, and so forth forever and ever for however many derivatives I want to take, right? Again, this is a series that goes until infinity, so I can differentiate as much as I want to, which we don't need to do, but we can. I can also integrate, okay? If I were to integrate, then instead of this stuff dropping, then we'll do a general integration term by term. So all of these things will go in the opposite order, right? So coming from here, this will be a n plus 1, and I will have a 1 over n plus 1 coming down because that's what we do when we integrate each term, okay? So if I were to integrate this series, it would look like this, okay? Now, don't worry about the integration. Again, this is just a review. We are going to focus on differentiating for our solutions. Okay, we're going to differentiate a lot, actually. So it's very important that you're familiar with these terms and what they look like and how to find them easily, because if you spend a lot of time trying to write these forms out, these problems are going to be very, very long, extremely long. So you don't want to get caught up here, because this is going to end up being the first step of the things that we do to solve. Okay. For series, we're always interested in whether or not a series converges or not. So we want to know things like, do they converge or diverge? Over what values of the real number line do they converge? Do they converge everywhere? Is there a smaller interval? Is it only a point? Things like that. So we're going to review those briefly because they're going to come up as we go through this chapter. So it's important that we kind of familiarize ourselves with that. So again, what does it mean to converge? It means that as we add up each value in our series, that we approach a single value. Okay. If we just keep increasing without bound, 1 plus 2 plus 3 plus 4 plus 5 plus 6, it just gets larger and larger and larger and larger and larger. We're going to diverge. We're going to go to infinity. Same thing as if we are adding negative numbers, right? -1 plus -2 plus -3, we're going to just start to diverge to negative infinity. However, if we add, let's say things like 1 plus 1/2 squared plus 1/3 squared plus 1/4 squared, those things don't increase very quickly. So as we add them up, we will converge to a single value. So that's what we're interested in. Okay, so we're not so much interested in what the actual sum is, okay, because these are power series. So it's not just a regular series. We're going to have obviously variables in here. So we just want to know whether or not these things converge at some point or not. Okay. So there's lots of ways to talk about these things, right? So again, we want to know when they converge. So we may converge on an interval that's closed, on an interval that is open, or a combination of open and closed. Okay, so we're going to have to kind of look at, we'll be able to find the interval easily, but then we'll have to look at the boundaries of that interval to depend on whether it's closed or open at the boundaries. Okay, so there's lots of ways to test for convergence. We're going to really focus on one or two. I'm only going to review one right now, but I am putting up a document for the the strategy for testing for convergence. On that document, there is a link. The link is not the stuff that I wrote in the document. The link has each of the individual tests that you use for convergence. There's quite a few of them. They all have their own conditions. I'm not gonna, that would be a completely separate video to talk about that, because it'll take a while, right? So just review those on your own. You guys should, it should be review, definitely. So just review your convergence. But this is one test that we will go over because you'll use it a lot. It's the most powerful test for convergence. So it's the only one we really need to use, but it doesn't work all the time. So you want to have a couple of other little tricks in your bag so that you're ready to handle some of the problems. Okay. So the test that we're going to go over is the ratio test for convergence. Okay. So this is a pretty strong test. It works very, very often. There will be times it doesn't work, which is fine. You just go ahead and approach the problem with another test, but this one will work a majority of the time. Okay. So what we're doing is we're looking at my series. So this a sub n is this whole thing. Okay. So this thing changes every time. The general term, it always changes. So for convenience, we're just going to call it a sub n. It's just some general term. So what we're looking at here is the absolute value of what happens when you start one more from your general term, divided by your general term, and then taking the limit of that as your series goes to infinity. Okay. So you're going to get out a value because this is a limit. Okay. If that value you get out is less than 1, you are absolutely convergent. Okay. Now, absolute convergent is stronger than convergence because if we have an alternating series where you alternate from positive to negative, you have to be absolutely convergent for those things to converge. Okay. If you have just all positive values or all negative values in your series, then you can talk about being simply convergent or not. So absolute convergence is sort of like a stronger convergence. Okay, so it's very, we're interested in this quite often. Obviously, if you're absolutely convergent, then you are convergent. Okay, so we generally use the ratio test because it covers more cases for us. If L is larger than 1, right, if this limit you get is larger than 1, then you are a divergent series. Okay. And if you are equal to 1, your test is inconclusive. You need to try something else. You can look at several other methods. There's the comparison test. There is the root test. The root test is actually very similar to the ratio test. There is the integration method. There's lots of things that you can do. So again, I have a document that talks about all of those things and a strategy for approaching finding out whether or not something is convergent or not. Okay. So for a given power series, there are only 3 possibilities. Okay, and this is in response to when you are convergent. You either converge at a point only. Okay, that point that we're centered about. You are convergent for all of x. Okay, meaning the entire number line, the whole real number line. So this upside down A, if you have never seen that, means for all, for every x that you can consider. Okay. And part 3 is that there's some positive number r, which we call the radius of convergence, that the series converges for. Basically, if you are centered about A, absolute value wise, is being less than r. Okay, so if you take your value x and you add a to it or you subtract a to it, you are within a distance of r for either of those cases. Okay, and you diverge if you are outside of that radius. Okay, so again, this is a radius of convergence. So you have your x value, you are r away on either side, and this bound that you're looking at where you're centered at has to be within that radius. As long as you're in that radius on either side, you are convergent. Once you are outside that radius on either side, you will be divergent. So this is when you have an interval. Okay, this is when you have an interval. So this is the distance between A is less than your radius. Okay, so this is a very, very standard math notation here. So you really need to be able to look at this and be like, oh, okay, I'm at a distance. My distance to my value is less than some number. Okay, this is very reminiscent of like an epsilon delta type of deal, but we're not getting into epsilon delta stuff, right? So for the first part, okay, when you're convergent at only a point, your radius of convergence is 0. There is no radius, right? There is no interval. You're only convergent at a single value, okay? Next is your radius of convergence is for every x, so your radius is infinity, right? You're convergent everywhere on the real number line. And then here, your radius of convergence is just this interval that we're talking about, right? It's the interval of convergence. All right, so let's talk about an example. We will try to pick a hard one, not a hard one, but one that shows a little bit of everything. Because again, this is review, so I'm not going to stick to boring results that just kind of are one-sided. So we're going to look at this series. Okay. Now, if you notice, this one starts at 1, and we've been talking about y starting at n equals 0. It doesn't matter where I start. It just depends on how I define my series. Okay, so here it starts at 1, big whoop. I could be at 5, right? It doesn't really matter. So for here, I'm saying that this is my series. Again, I'm not saying this is a function. It can be. Well, I mean, it is. It definitely approximates some function. I don't know what function it is. But we're just looking at this as a series. Okay, I have this binomial to a power. I have this exponential on the bottom, and I have the square root on the bottom as well, right? So again, the first thing I want to do is I want to test for convergence. So I'm going to use the ratio test. I'm going to take this and I'm going to bump it up by 1. I'm going to bump this n by 1 and this n by 1, and I'm going to divide it while taking the square root, the absolute value. I'm going to divide it by this term. So I'm just saying this now because I do like to write a lot, but I'm not writing everything. So I'm going to have this term with n plus 1 on top divided by another fraction. So a fraction divided by a fraction means that you multiply by the reciprocal, right? So it's going to look like this. I'm taking the limit as n goes to infinity. I have the standard form here with n plus 1 everywhere. And then I'm going to multiply by this, but flipped over. That's why this part is on top and this part is on bottom, right? Again, this is review, so hopefully you guys remember this, but it's easy to go straight to this form instead of writing this over, this plus 1 over itself, and then getting here. Just know that you have the plus 1 form, and then you'll have the reciprocal of your general term here. So this is going to simplify nicely. So I'm going to be subtracting powers here. I have n plus 1. I have just n here. So the powers subtract. That's going to leave me with 1 on top. Same thing here. N, I'm going to minus n plus 1. So that'll leave me with 1, 5 on the bottom. Square root of n plus 1. That does not simplify. I can throw it all under 1 square root, but it's unnecessary. But those don't cancel at all. Those are completely different. So this is what my limit will look like. I'll have the extra 2x minus 1 on top. I have the extra 5 on bottom. And then I have the square root terms that I could not get rid of. As the limit goes to infinity, for n, I'm not looking at x at all, only the n's. Okay. This is a number with a larger number on bottom. It doesn't matter if it's square rooted or not. The denominator will grow faster than the numerator, which means that this will tend to go to 0. So the limit of this goes to 0. The limit of this doesn't do anything because the limit is in respect to n. So what I'll be left with is just the absolute value of this. Okay. So I prefer to write things in sort of a product form. Okay. A fraction times the thing that I have. You can leave it like this inside of your absolute value. I don't really care. It's a matter of kind of preference at this point. Okay. So I need this thing. Okay. Again, this is what I need. I need x minus a in the absolute value to be less than r. Okay. So for right now, I need the limit of my ratio to be less than 1 in order to be convergent. Okay. So this thing is convergent if this thing is less than 1, and that's dependent on x. But remember, again, like I just said, I need absolute value x minus some value less than some radius. Okay, I want it to look like this. So what I have inside my absolute value does not look like this. Okay, I have a bunch of stuff with my x. I need to isolate this x. Okay, so that's how I figure out what my radius of convergence is, by isolating this x. So the first thing I'm going to do is I'm going to multiply everything times 5 to clear this 5 out. Okay, so I got 2x minus 1 is less than 5, right? Now the next thing I need to do is divide everything by 2 so that I can have it as x minus some value. It could be x plus some value, that's fine, right? It would just be an opposite value here. But I need this x to be isolated. So divide everything by 2, and this is what I have. So that means my radius of convergence is 5/2. Okay, and then this gives me 2 equations, right? So again, this just tells me what my radius is. Solving this will give me the boundaries for my radius of convergence. So my radius is 5/2. I'm centered at 1/2. So I need to say if I'm at 1/2 and I add 5/2 over here and add 5/2 over here, what values do I have? So I'm centered at 1/2 and have a radius of 5/2. What are those n points going to be? To do that, we just set up an equation, right? This is an absolute value. We just turn it into 2 separate equations. First equation is just your standard equation where you drop the absolute value signs. The other equation, you multiply everything by a negative. So this turns into negative 5/2. And then you switch the sign and you take the absolute value away, right? So these are the 2 equations that you have, and then you just solve them both, right? So I add 1/2 here, I add 1/2 here, I got x is less than 3, and it is more than -2. So those are my bounds, from -2 to 3. So that's my radius. I'm centered at 1/2, okay? And I'm convergent as long as I'm inside of -2 and 3. However, I don't know if I'm convergent at 3 or if I'm convergent at -2. I need to check my boundaries, because remember, this interval that I have for convergence can be open, closed, and a combination of the two. You will always end up with an open interval here because of the way this form looks. It's always that I have to be less than my radius, less than my radius. I'm always going to get a strictly less than, greater than here, right? So again, in order for this to be open or closed, I have to actually check the boundaries, right? So don't forget to do that. It's a very common mistake for students to not consider the full problem, so I have to check the boundaries. Okay, so in order to check the boundaries, I'm going to start with x equals 3. So what I do is I look at what happens when x is 3. I take my series, I'm going to plug in 3, right? And then I'm going to see if the resulting series I get when I plug in 3 to my original series is convergent or not. If it's convergent, I get a square bracket. If not, it stays open. And then I do the same thing for -2. Okay, so real quick, if I take 3 and I plug it in, this will be 6 minus 1 will be 5n. So I'll have 5n over 5n. When I do -2, I will have -4 minus 1 is a -5n. Okay, so let's just go ahead and do that. X is 3. That gives me this series as a result. When I simplify, obviously this cancels. I have a 1 over n to the 1/2. Now I can do my ratio test all over again because I need to see if this is convergent or not. However, this is a very, very standard result. Again, this is why you should review your the handout that I have for you, because the ratio test is kind of overkill here. This is a p-series, okay? It's a p-series where p is 1/2. If your p-value is less than 1, I should say this again, 1 or less, okay, then you're divergent. You need to have a p-value larger than 1 in order to be a convergent p-series. So this series diverges, okay, because it is a divergent p-series, this is not larger than 1, right? So I diverge at the right endpoint. So now I check the left endpoint, x equals -2. I do the same thing, I plug in -2 everywhere, okay? I try to simplify this, so it's not necessarily the same. The only difference is a sign, right? So this is going to simplify to this. Again, remember, square root of n is just n to the 1/2, right? So I could have wrote this as -1n over square root of n. It doesn't matter. Remember what I said before, that when you are an alternating series, so again, this is going to be positive or negative depending on your value of n. So the first value here will be negative. The second one will be positive because you have a -1 squared. So it's going to alternate negative, positive, negative, positive, negative, positive. So you cannot use your p-series test here because p-series is for a strictly increasing series. Sorry, a strictly positive or strictly negative series. It does not work when you have an alternating series. So what we're going to do here is we're going to just do the ratio test. Again, for alternating series, ratio test is the best thing that you can do. So here we will just apply our ratio test. So I'm having the +1 form everywhere. Okay, I put this back into the square root form just because it's easier to look at. And then I have this, right? So again, n plus 1 and the n. So this will turn into a -1. Then this thing doesn't go away. Okay, but the -1 doesn't really matter at all because I'm inside of an absolute value. So who cares if it's negative or not? Because eventually it's going to go away, right? We saw this already. This goes to 0. 0 is less than 1. So my ratio test gives me a limit less than 1. So I'm convergent at this end. So on one endpoint, I'm convergent. On the right end, I am divergent. So what does that look like? I have a radius of 5/2. My interval of convergence is from -2 inclusive to 3 exclusive, right? So that is our overview of series. Okay, we're not done, but that's our review. Okay, we're going to go over a couple of things real quick that is going to help us for solving our DEs, which is going to be in the next video that I make for you guys. So these methods here, this is still a review, but it's more specific and more tuned in to the stuff that you're going to actually be doing. So what we're doing before was just like, hey, you guys remember this is what things look like in the series world. So now we're going to actually start playing with series a little bit. This stuff may be new to you. You may not have seen these before because this is not the focus of series in Calculus 2. The focus of series in Calculus 2 is to figure out if things are convergent or divergent and when they converge or not. So now we're going to talk about how to manipulate these things a little bit, which is what we're going to be doing for solving DEs. Okay. So we're going to talk about shifting the index. Okay, so I'm sure you're aware that you can represent the same series multiple ways, right? If I wanted to say, hey, I want to call this n equals 0 instead, I can change how I talk about the n inside of here so that it is the exact same series, and when I start evaluating things, the numbers in my series don't change at all, right? So if I change this, then I change this, it'll be exactly the same, right? We kind of saw that earlier when I showed you that n equals 0 was the same as n equals 1 after you take the derivative, right? So we're going to be talking a little bit more about things like that, not that exactly. That's a very, very basic idea of what we're going to go over right now. We are going to want to combine series. Okay, we're going to have several series that we're playing with at one time. So it's going to be a way, way more convenient for us to add them together to have a single series, right? But in order to add series together, we have to have some things that match up. We'll also be looking to pull out common factors and things like that. So we're going to want to get a few things to match up, namely the starting index and the index for the powers of x. Okay, we want both of those things to match up. So that's going to take a little bit of finagling to do. Okay. So let's start off with a couple of examples. So I'm going to give you guys 3 examples, and we're going to work through all 3. They're going to go from easier to harder. Each time I'm going to introduce a new level of complexity for us to kind of discuss. Okay, so the first one is the easiest case. Okay, everything is fine, right? So here I have 2 series. The indices match. Okay, the exponents match. Okay, if I plug in 2 here, these x's all start at the same value, x to the 5th power. The indices are the same, the powers are the same. I can combine these very well. Now, I don't need these powers to match up in order to add them together, but it makes things a lot more convenient. Okay, I do need the indices to match. So, since these are both sums starting at n equals 2, and they both have x to the n plus 3s, I can just add them as a single series where the general term is this plus this, right? This plus this. This whole thing is my new general term. Okay. Now, if you notice, both of these have a Cn x to the n plus 3. Cn x to the n plus 3. So this simplifies very nicely. I can pull those things out as a common factor because they're in every single term, basically. And so I have n plus 2 times Cn x plus 3. Okay. So when everything is fine, everything matches up. Especially if I have common terms everywhere, it's very, very nice because I can, instead of taking it as 2 series or even 1 series with a long general term, I can simplify it down. And that's what we're going to be looking to do. What we're going to need to do though is there's going to be some work we have to do to get it to look like this where everything is fine. And that's what we're going to focus on. Okay. So this would be the last step of us combining series. Alright, so let's add one more level of complexity here. Alright, so let's say that our starting indices are different. Okay, so here I have n equals 0, I have n equals 2. Notice the values for the x's are the same though, so it's the exact same thing I had up here. I just shifted the indices, right? So it's nice because everything still matches up, right? So since they're starting at different indices, right? So again, if I plug in 0 here, I'm going to get x cubed. If I plug in 2, I'm still going to get x to the 5th. My indices don't match. So I would like this to be n equals 2. I'm not just going to magically say, let this be n equals 2. What we do is we pull out a couple of values. Okay, so I like these to start at the same place. So I'm going to pull out the first 2 terms here. So what do I mean by that? I'm just going to evaluate n equals 0. I'm going to evaluate n equals 1. And then I can then add from n equals 2. Okay, so 0 is C0 x to the cubed, 1 will be C1 x to the 4th, and now this will start at n2. Then I have this value here. Notice now that this is exactly what we had in number 1, so I can replace that with the sum term. Okay, so the 2 terms I pulled out plus the single term, this should be a plus. I guess that disappeared also. Okay, so just imagine that there's a plus here, right? I'll fix that in the write-up, so I guess that's 2 things for me. But basically, yeah, I'm adding the 2 terms I pulled out plus the single series that I have, okay? So in 3, this is when everything is wrong, okay? The indices don't match, the powers don't match, right? So here I have x to the n plus 3. Here I have n minus 1. This starts at 2, this starts at 0. The powers aren't the same, right? This starts at x cubed. This is going to start at x, just x. So I'm going to shift these things. So we're going to have a pretty lengthy, it's not too long, but it's quite a few steps, about 5 steps. So the first thing I'm going to do is I am going to pull out terms until these match. So again, this starts at cube. This starts at just an x. So I got to pull out terms from this one until the x's match here. Not the way this looks, just the starting value of the power of x. Okay, so I'm going to pull out terms until the first index on each series, the starting index, makes it so that the powers are the same. Okay, so again, this, if I evaluate here, will give me an x cubed term for the first term. If I evaluate this one, when I plug in 2, I will get just an x as the power for my first term. So for this one, I need to pull out 2 terms until it matches up. Okay, so we pull 2 terms from this series. So I pull out my first 2 terms. So I plug in 2, I get 3 C2x, and then that's going to step up by 1, right? So if this was 3, that means this will be 4. If this was 2, this will be 3. If this was a 1, this will be a 2, right? This is going to keep going up by 1. So now my starting indices starts at 4. I have a couple of terms trailing, and now when I plug in 4, I will get an x cubed term here. Okay, so that's the first step. Okay, I want the powers to match up, so I pull out terms wherever I need to so that the powers match up in both or all 3 or all 5 of my series that I'm working with. Okay, so right now this is what I have. I have these 2 terms that I pulled out. I have this first term that starts at 3 already, plus my new term for this, right, starting at 4, so that I have an x cubed term. Right, so now this is the series that I'm working with. Okay, I'm going to make a different k substitution for each series. Okay, I'm not going to call it k1, k2, k3. I'm not going to do that. It's just a single k, but the k for the first series stays as that k. The k for the second series stays as that k. The k for the third series stays as that k. I don't differentiate between them. They're all just k, but they represent different things in each series. So you want to just, when you're doing your work, write it down, keep the notes, right? We make k equal to the power index for each series. This part, okay? So for this series, k will be n plus 3. For this series, k will be n minus 1. Okay, so k is n plus 3 for the first one, k is n minus 1 for the second. So the powers of x on your general term is what you make your k substitution. Okay, my third step is I take this, I could have wrote this all as step 2, but we're trying to break it down, right? So I'm going to take this and I'm going to call this n. Okay, I'm going to solve for n here and solve for n here. N is k minus 3, and here n is k plus 1. So all I'm doing is adding 1. So I have n is k plus 1. Here I subtract 3, n is k minus 3. All right, I'm going to substitute this new n everywhere in the appropriate series, right? So this goes in the first series, and this goes everywhere I see n in the second series. Okay, so then when we plug those into our values, it's going to look like this, right? So everywhere in my first term, everywhere I saw n, I replace it with k minus 3. So k minus 3, c to the k minus 3, x to the k minus 3, right? So everywhere I replace with minus 3 everywhere. So for the second one, I have n is k plus 1. So everywhere I see my n, I replace that with k plus 1. So n is 4 is k plus 1 is 4. Right, n plus 1 is k plus 1 plus 1, right? So I just replace that everywhere. And on the next step, what I'm going to do is I'm going to simplify all these values. So I will add the 3 over. This will disappear. I'll subtract the 1. I'll combine this, and I'll move this over. Okay. So now my indices match on my series, and my powers of x all match up as well. Okay. So now I can combine these down into a single series, just like we did in example 1. So when we add our values together, we take our original series, this is what we started with, and this is what it's going to look like when we add all of our stuff together. So I have the terms I pulled out, plus the single summation of these 2 pieces. Nothing combines because I have different indices for the constant terms, but I can write them all as one series, one general term with a common term of x to the k pulled out.